Welcome back, my friends, to the show that never ends. This is Dr. Me at the Actuarial Academy, and today we're going to introduce and talk about permutations and combinations. I'm going to use a somewhat informal approach and not use technical definitions, but rather something that's more intuitive, appealing, using English language. So let's jump right in here with permutations. So a permutation is the number of ways to order or arrange a set of objects. So here the key word that you must remember is order. So order is most certainly important in that we care and we want to count, or at least include in our count, the different ways of ordering the object. So we'll do an example here in a moment. If you want to arrange, say, books on a bookshelf, and you have your history, math, and biology books, and you arrange those books, well, history, math, biology is one arrangement, or you could have your math book first, and then history, and then biology. It's the same objects, but they're arranged differently. Likewise, you have biology, math, or history, the complete reverse of the first arrangement I mentioned. So permutations respect order and include the different orderings in the total count for the permutation, as opposed to, and we'll talk about combinations later in the video, and combinations, actually order is not relevant. So an example, another example for permutation where order would be relevant, say horse races. Say you have 10 horses and they're involved in a horse race, and you're going to give out top 3 prizes, 1, 2, 3, first, second, and third prize. And so here order is important, because if Lucy gets the first prize, is different from, say, Lucy getting the second prize or the third prize. Okay, so you have to be careful in counting, combinatorics. You need to make sure whether order is important or not. So let's emphasize this with an example. You have 3 books. Okay, you have 3 books you like to arrange on your bookshelf. So now we're going to actually learn how to count a permutation. It's actually fairly straightforward. And again, we'd like to know how many arrangements are possible. So in this problem, it's fairly clear that order is important, and I've already discussed, as I was introducing the definition of permutation, why. So we could actually enumerate these, but if the list, or if we had many more books than just 3, the enumeration would be a little intractable. So let's just talk through it and see if we can just count it mathematically without using enumeration. So you can think of the 3 books being available to be arranged on your bookshelf. Well, you'll see that initially, if we were to grab one, we have 3 choices. And then once we have chosen the first one, we only have 2 choices left, and then finally only 1 left, to where we have 6 total arrangements possible. Now, this has a special form to it, 3 times 2 times 1, and whenever you see this form with a number starting here and you subtract 1 from each value afterwards, this just is written mathematically as 3 factorial. Has like a exclamation point after the 3. Stands for 3 factorial. So again, what we have here is initially we have 3 choices, and this will work in general if you had, say, 10 books or even 100 books to arrange on a bookshelf. The answer would be 10 factorial or 100 factorial respectively, and it would literally count all possible orderings or arrangements of those books for the bookshelf. And again, what's important is order. So we are counting order. And so another way to look at this is to do a diagram, if you're more of a visual person, and we'll let H indicate history book. So initially we can have a history book chosen, or math book, or the biology book, right? So after you choose the history book, we can have two more choices, the math book or the biology book. Okay, then after that we only have biology or math book. Okay, and likewise here. We would have the history book as a choice after the math book, or biology. And then we only have the biology or the history book left in these situations here. And likewise here. Math and history book, or the history and the math book. So here we've actually enumerated all 6 possible arrangements is given there. So this kind of emphasizes how we have 3 choices initially. That's why we have 3 here. And then 2 more choices there for a total of 6. And of course then 1 more that we just tag on for the remaining book times 1, which gives us our total 6 arrangements. Now let's do another example involving a horse race, where we have, again, as I already mentioned, 5 horses. How many different outcomes or races are actually possible? So what we're saying here is, if you have 3 horses winning, then it matters who gets first, second, and third prize, which is the same thing as saying order matters. So let's further suppose we have the horses' names as follows. I'm putting a little different spin on the problem here, just trying to show you different flavors in which these problems can arise. But here we have 5 choices for first place, 4 choices for the second place, and then 3 choices for third place, which here is equal to this is equal to 60. So this is similar to this problem here, except we stop at 3 because we only have 3 horses that can win. But it's the exact same principle over here. So the other 2 horses you can think are just kind of left out. Okay. So let me extend this problem just a little bit, and I want to now motivate this concept of a combination. So far we've been talking about permutations, and suppose now we didn't care about the first, second, and third prize, but instead we only care about what subset of the 5 horses can end up winning. So we want to actually count the total number of subsets of size 3 from the total number of horses in the race, 5. Again, independent of the actual way in which they might win, first, second, or third. We just want to know which of the 3 horses could possibly win in the total number of subsets. So I'm going to go through a little derivation here to motivate or derive how you actually count combinations or subsets of horses, and we'll actually do a formal definition of combinations here in a moment. I'm just kind of talking through this with you. So note, this is how it works. And just to give you a little bit of a foreshadowing, what we're going to do is, you know that when we counted back here the total number of outcomes possible with respect to the order, in the sense that we did care about first, second, or third prize, what we're going to do is we're going to take out, so to speak, or divide by the number of different ways that you can actually order the 3 horses that could win first, second, and third prize. And that would eliminate the permutations that are double counting or counting more than once the different winnings. So that'll be a little clearer here. We going back here, we realize, okay, there's a total of 60 possible races or outcomes. So if you were to actually enumerate all possible 60 outcomes, what you'll find is that you're actually taking each possible subset of the 3 horses out of the 5. Okay, and for example, Lucy, Rooster, and Katya. And you are counting the different ways of permuting or ordering these to take into account the different ways that they could possibly win. And just for completeness, let me just write this here. Okay, that's one permutation. Another one is, we know that there's actually 6 of these, or 3 factorial. Okay, and let's take another subset, Rooster, say, Spinoza, and Cogito. And this exact same thing is true. We could write out those 3 factorial permutations corresponding to that subset, and that would also be 3 factorial. Okay, and of course we could do that in principle for all possible subsets. Okay, now what that tells us then is that, so here's the big takeaway from this then, is that the total number of subsets of 3 horses times 3 factorial should give us then our 5 times 4 times 3, or 60, which is again total number of outcomes to the race with 3 horse winning first, second, and third prize, where order again is important. Okay, and this is the where order is important part right here. Set 3 factorial. Okay, but what we were interested in, at least for this part of the problem, was just the total number of subsets of 3 horses. So what that means then is that our total number of subsets of 5 horses taken 3 at a time is equal to the total number of outcomes, including or respecting where order is relevant, and then we take out the number of ways we actually can permute the 3 horses, because we no longer care about the first, second, or third prize. And this is just equal to 10. So let's investigate this piece just a little bit further here, okay, and see if we can rewrite this in a little better way. I'm going to just go ahead and extend this, make it a little nicer, okay, and call it 5 times 4 times 3 times 2 times 1. Okay, so we're tagging on a little bit there, and then I'm going to leave the 3 factorial there, and then just 2 times 1 here, because we can't upset the numerator, we have to do both. So we're basically doing the multiply by 1 trick. But look, this now can be very nicely written as 5 factorial divided by 3 factorial times 2 factorial. Okay, probably something you're familiar with, which again is just equal to 10. And that's the number of combinations or subsets of 5 horses taking 3 at a time. And this leads us to combinations. So I've kind of derived this notion of combinations from permutations. So let's do a loose or informal definition of combinations. Okay, so loosely speaking, combinations is basically a number of subsets of a given size from a set of objects. So let's illustrate that with an example. Making pizza. Something everyone likes. So let's say there are 10 toppings available, and the question is how many 3 topping pizzas can be made. So let's talk through this. In the context of the problem, we don't really care the order in which the toppings are actually placed on the pizza. If we did, that would be a permutation, but clearly at the end of the day, after the pizza comes out of the oven, we don't really care how it was put on. We just want to know if 10 toppings are available, how many different pizzas can be made that have 3 toppings. So this is a combinations problem. So to use a similar derivation as we did here, you can think of it as, first of all, counting, if order actually did matter, the number of ways to make the pizza. Okay, it would be 10 times 9 times 8 times 7, which is a permutation, which of course again takes into account order. So what we want to do then is, since we've double counted, or not double counted, actually counted the number of permutations of taking 3 toppings, and we are doing 3 toppings. So why did I write that last number there? Sorry, back up there. The number of ways to permute those 3 toppings, we've counted that many times, so we need to undo or divide by the number of ways to permute those 3 toppings, because we only care about counting it once. And so that's actually our answer right there, whatever that turns out to be. So again, just to make this look a little cleaner and to look more like the formulas that you might see in the book, you can write this as 10 factorial divided by 3 factorial times 7 factorial. And that's the combination. So that's taking 10 toppings available and counting the number of 3 topping pizzas that can be made. So I'd like to do one final example to illustrate both combinations and permutations in one problem. So say we have a 10-digit keypad to open up your car door, and let's say that one must enter 4 digits, a 4-digit code. So for the first part, let's find number of passcodes. So first find the number of passcodes possible if order matters or is relevant, which it normally is in opening a car door. Usually passcodes are order sensitive. So if you enter 1, 2, 3, 4, that would be a different code than entering 2, 1, 3, 4 or 4, 3, 2, 1. Okay, so this is realistic. If we have 10 digits, this would just be 10 times 9 times 8 times 7. Okay, so this is a permutation. It matters if order is different, so we need to count all the different orderings, and that's the final answer. So for part B then, so let's do the same thing here. Find, okay, so here we're going to change the problem a little bit, and we would like to know the number of passcodes possible if order is not irrelevant. So here, if we were to enter 1, 2, 3, 4, the door would open the same way if we entered 2, 4, 1, 3, say. It's kind of ridiculous to have a car combination like that. But let's say we did have a manufacturer where all it mattered is that the digits matched after you entered them, but didn't really care about the order. So again, you start out the same way we did before. We count the total number of permutations, and then we take out all the extra counting of the permutations that we didn't want. So you just divide by 4 factorial. And as I always do, you can write this as 10 factorial divided by 4 factorial times 6 factorial. Okay, and that's the end of the review of permutations and combinations. Thank you.